So this is going to be a video on chapters 9.1 and 9.2 for stats about the inferences about two proportions. So basically what this chapter is and what this entire section is for chapter 9 is basically taking the stuff from chapter 8 and applying it to cases where you're comparing two populations rather than just comparing a population to a value. Like in the previous chapter, we might have said, okay, test the claim that 30% of people in the population have blue eyes. Well, now we're going to do something like test the claim that this population in this state has more people with blue eyes than this population in this other state. So we're comparing two populations rather than just comparing one population to a target value. That's what this chapter, this whole section here is about. And again, we're going to do it for percentages, going to do it for means, and going to do it for standard deviations. So the requirements are still the same for the most part. We just have two populations this time, but they both have to be simple and random, and they have to have at least 5 successes and at least 5 failures to, again, meet these thresholds here. So same thing as before, just both populations have to satisfy them now. We're going to have a little bit different notation because we have two populations to go off of. So p hat 1 is simply, let me get my pen here. P hat 1 is simply the sample 1 proportion. So it's the first sample proportion. It's the number of successes in your first sample, right? Number of successes in your first sample. So that's, again, when you take the percent of successes in the first sample, I should say that. Percent of successes in the first sample. So that's when you take the number of successes in your sample divided by the number of values in your sample, and you get p hat 1. Right? So again, if you have 10 people in your population out of 100 that have blue eyes, your p hat 1 would be 10% or 0.1. N1 is the total number of, I'm going to get my marker here, there it goes. N1 here is the total number of the first sample. So size, I guess you could say, of the first sample, right? So it's the size of the first sample. So 100 people you surveyed from the first, 1,000 people, 12,000 people, don't care what. It's just the size of your first sample. Just a normal average everyday N. And X1 is the number of successes, pardon the spelling, in the first sample. So again, you survey 100 people in one state and you get 10 of them with blue eyes. 10 out of 100 is your sample proportion. And Q hat is the percent of failure, obviously again in the first sample. Oops. And the formula for Q hat 1 is the same as before. You just take 1 minus P hat 1. So 1 minus P1 hat. And again, this is the same notation we did before. It's just that now we have a little 1 down here to denote that's from the first sample, and then obviously we can use 2 to denote if it's from the second sample. So again, we're just comparing two different samples and two different populations in this case. So because of this, we now need a pooled sample proportion. So a pooled sample proportion is basically the sample proportion of both values combined. So you have the number of successes in the first sample plus the number of successes in the second sample over the total number of items in the first sample plus the total number of items in the second sample. So it's just combining both population values together, essentially. And again, you can do 1 minus this to get your Q hat. And that's going to be used in this formula here. So this is a big formula for the test of two proportions. This is how you get your test stat. Remember, your test stat is kind of what we use to, sorry, I drew a blank there. Your test stat is what you use to help you decide whether you're going to reject or fail to reject, right? We compared our test stat to our critical value, right? And see if it's in the rejection region or not. This is based off of the null hypothesis that P1 minus P2 is equal to 0, or put another way, this is based off the null hypothesis that P1 is equal to P2. So we're going to be using this as our new null hypothesis. Before, in chapter 8, remember it was like P equals 0, or P equals 0.5, or P equals 0.03. Right? We had a certain value that P was supposed to equal in our null hypothesis. Now, it's always going to be P1 equals P2 because we're comparing two populations and we're always going to assume that they're the same. And then we can say, well, we're going to test the claim that one is more, one is less, or that they're not equal. Right? So we can, this is always going to be our null. Our HO is always going to be the same setup, right? And again, we're using z-scores. So this is a z-score test because we're testing proportions, so no need to worry about that. You don't have to memorize this formula. I will give this formula. But actually, truth be told, we should never have to use this formula ourselves because we can have our calculator do it. So I'm going to show you how to do this in your calculator in this next example here. These are the button presses to go through. Once you get to the menu, it's really not that hard to do because it kind of tells you exactly what it needs in order for it to function. But let me show you an example of how to use it in your calculator, okay? So We're testing two different uh, uh, treatments for a surgery. Sorry, I got blank there. Two different treatments for a surgery. We can test a surgery treatment or a splint treatment. So we have people with carpal tunnel syndrome, and we want to see which treatment is better. And so we see that the surgery treatment has a 92% success rate, and the splint treatment has only a 72% success rate. So when you look at when you're looking at that there, you can think, well, surgery has a much higher success rate than splint. Obviously, surgery is the way to go. But then somebody else can say, well, hold on, wait a minute. They both have roughly the same success number, but splint just had 83 more people tested, or sorry, splint had 10 more people tested than surgery. So it's not really a fair comparison because there's more people that tested for a splint treatment than there were for a surgery treatment. So this comparison is not all that fair. So maybe this relationship here isn't as cut and clear as it seems. So maybe that's not maybe there is no difference. Well, we have to test for that, right? So we have to test to see, is this going to actually is surgery actually a better treatment? Is there evidence to believe that surgery is actually a better treatment than a splint in this case? Okay, fair enough. So my H1 is going to be that there's no difference, right? That P1 is equal to P2. The percent of successes for the surgery treatment is the same as the percent of successes for the splint treatment. There's no difference. But my claim is that no, surgery is actually a better or a higher percent of success than the splint. Okay, so that's my claim here, right? So, whoop, my bad. Sorry, go back there. So that's my claim, and I want to see if this is true. So my value hasn't changed. I still need to get a test stat. I still need to get a z-score that I compare to my critical value or a p-value, one of the two. So here's the data that I need. I'm going to need my p hat 1. I'm going to need my p hat 2. I'm going to need my test stat, my ts. I'm going to need my critical value, and I'm going to need my p-value. Right? Those are the things that we're going to be looking for here. Now, as we get used to these, we don't necessarily need all of these every single time, because as we get used to them, we'll start to see that, oh, well, if I'm going to do this comparison method, I only need these two items here. But for right now, we're just going to get all four types of items that we need, and then later on, we can kind of pick and choose which ones we want to actually invest in. Okay? But as I said, we can usually do all this in our calculator. Now, P1 and P2 are kind of given for us here, right? P1 is 0.92. 0.92. And P2 is 0.72, because that's surgery and splint success rates accordingly. So this is P1, this is P2. This here would be X1, X2, N1, and N2, because again, we have number of successes, number of tries, number of successes, number of tries. And then again, P1 and P2, whoops, hat down here. Okay? So now we're going to go to our nifty little calculator. And the way you do this is you go to stat, because we're in stats class. You go to calculate. You go to tests. Now you can go to test here. You don't have to go to calculate. You go straight to tests. You go down to where it says 2 prop z test, because you're doing a 2 proportion z test. That's why you go to 2 prop z. So click that. It's going to ask you to enter in the information you should have from your table or your word problem, right? So 67 people got surgery out of 73. I should say 67 people had a success out of 73 versus the 60 people who had success out of 83 for the splint. Whoops. Out of 83 for the splint. And I'm testing to see if P1, my surgery, is bigger than P2. So this is my alternative hypothesis. This last line here is, what is your alternative hypothesis? And this is going to ask you to do one of two things, either calculate or draw. Now, if we click calculate, it will give us kind of this information here. It'll tell us what my p hat 1 and p hat 2 are. Boom, boom. It will tell you what your z-score is. So this is your test stat z-score. This z right here is your test stat z-score. So 3.1225. So 3.1225. That is my test stat z-score. That is, if I go back here, that is it doing this big old formula for you. It does all that work for you. No harm, no foul. It's happy to do it. So you get your test stat z-score that way. And it also gives you a bunch of other information too. It says that p is equal to 8.9694 blah, 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 e to the negative fourth. This is your p-value. This is this PV right here. So I'm going to do this right. 8.964. We'll put 8.965 just because I don't want to round up to 9. So 8.965 0.965 times 10 to the negative 4, was it? So that e negative 4 means times 10 to the negative 4, so negative 4. And so if we multiply this out, this means move the decimal up 3 times. Boom, 2, or sorry, move the decimal up 4 times. So 1, 2, 3, 4. You get 0.000896.5. So that is your p-value. And your critical value, in this case, you actually have to figure it out. So it actually does not give you your critical value, because remember, your critical value is based off of your alpha. So my alpha is 0.05. I'm doing a, let's see here, I'm doing a right tail test. So my critical value would be negative 1.645, right? Because again, my critical value my critical values haven't changed from from when we did confidence intervals, really. So there's no trickery there. I just look up 0.05 on my z-score table. I find out what the z-score is for 0.05, and it ends up being actually be positive, right? Some of you are probably yelling at me like that because it's a right tail test. So I'd use the positive version of this number, positive 1.645. Okay. So again, my z-score hasn't changed since, or sorry, my critical value. I keep saying z-score. I should probably tell you what the z-score is. My critical value hasn't changed since the beginning of time, essentially. But everything else is gotten on my calculator here, and I can go straight to comparison. If you want to draw it, the draw function doesn't do much. It just kind of shows you the nice little graph, essentially. So draw, and it just kind of, there you go, shows you the graph. So it still gives you the same information. So here's your test stat right here. Here's your p-value right here. They kind of rounded your p-value in this case, but that's essentially the estimate of your p-value. It doesn't tell you what your p hat 1 and p hat 2 are anymore, but again, you're usually given that from the table anyway, and those are pretty easy to figure out. But it just shows you the nice little Humpty Hump graph, and you can go ahead and trace along the graph if you want to, and you can find out different points there. I guess I thought you could trace along this, but maybe I'm clicking the wrong button. Anyway, it just kind of shows you all your values and whatnot. So again, nothing special there. Usually if you do the calculate function, you get all you need. And then down below, it shows you again the information. If it shows me, it's not wanting to do that. Darn. Okay, usually it will show you your N1 and N2 again, but for some reason it didn't want to do that. So, but then I can go straight to comparison, right? So is there enough evidence to show that surgery is more successful than splint? Well, my p-value, if we use our p-value comparison, my p-value is 0.0009 essentially. That is definitely less than 0.05. So in this case, we would reject HO, and well, I probably should put that over here. We would reject HO, and we would support my claim, because my claim is that H1 is bigger. This is my claim right here. My claim is H1, or my P1 rather, is bigger than P2. That surgery has a bigger percent of success than splint. And this certainly shows that fact. Quite comfortably too, because 0.0009 is a lot smaller than 0.05. So it's a quite comfortable rejection as well. So again, this whole work is mostly going to be done in your calculator. Your calculator is going to do most of the heavy lifting. You just need to make sure you can interpret it. Let's try one more. Okay. So in a USA Today article, and this is from a few years ago, said that we're testing the effects of a vaccine. So it says in a trial involving 1602 children, 14 of them out of 1070 who got the vaccine had the flu. 95 of them out of 532 who got the placebo got the flu. And so it says that the nasal spray cuts the children's chance of getting the flu. It doesn't tell you by how much. It just says it cuts the children's chance of getting it. It makes it less likely for them to get the flu. Well, let's see. Again, the effectiveness of the vaccine is kind of an important thing nowadays. If you're living in 2020 or 2021 and you're watching this video, that means that you're probably in the midst of a corona pandemic or whatever they say. Pandemic, epidemic, I don't know what the word is. But again, vaccine efficacy and vaccine effectiveness is kind of an important topic nowadays. So we want to make sure that our vaccines are actually effective as we say they are. So let's test this theory here. Let's test to see if this vaccine actually is working. So let's state our hypotheses. So my HO is that there is no change, right? That P1 is equal to P2, that the vaccine has no effect. I should probably put colon here, not equals. My H1 is that no, the people with the vaccine had a lower infection rate than the people who did not take the vaccine. right? Does not want to work with me today. So that is my claim. My claim is that the people who got the vaccine have a lower infection rate than the people, whoops, than the people who did get the vaccine. So this is my claim right here. Okay? So now I need to figure out my different values here. So p hat or p1 and p2. I should say p hat 1 and p hat 2 to be honest. Again, I know we're going to do a lot of this in our calculator, but it's good to list out your values first. That way, at least for me as a teacher's perspective, if you're doing your work and you enter it all in the calculator and you get the wrong answer because you entered in the wrong information, I need to know where you went wrong so I can see whether you went wrong on a small way or a big way. Otherwise, I just assume you went wrong in a big way. So make sure you list out all the information you're plugging in first, which means you have to be able to find it, before you go ahead and just enter it into your calculator willy-nilly. So p hat 1 and p hat 2. Well, if we read the problem, if we go back for a second and read the problem, it actually tells us my p hat 1 is 1% and my p hat 2 is 18%. So 0.01 and 0.18. I should also probably put my x1 and my n1 here because that's what I'm going to actually enter into the calculator, right? So my x1, my n1, my x2, and my n2, that got me these numbers. x2. And that you have to be a little bit careful because they do throw actually a lot of numbers at you. And it can be easy to get these mixed up like I did when I first did this problem. So let's see, where's my x1 here? So it says, in a trial involving 1,602 children. Now, this is the first mistake people make. They think that this is their n, but it's not. This is how many people took part in the study. 14 out of 1070 got the vaccine and developed the flu. So my first thing here is 14 out of 1070. Right? Again, getting the flu is not necessarily a success, but in this case, since we're tracking how many people got the flu, yes, it's going to be a success, quote unquote, in our situation here. The next one says that 95 out of 532 got the flu who had the placebo. So 95 out of 532. Whoops. Get back here. So 95 got the flu out of the 532 who got the placebo. So again, there's a lot of numbers in the problem. It's helpful to write out which numbers you're going to put in your calculator. That way you don't actually put in that like 1620 or whatever when that doesn't belong there. Okay. So let's go to our calculator and enter in this information. So we go to stat, test, to prop z. We had 14 out of 1070 get the flu when they had the vaccine, and 95 out of 532 get the flu who had the placebo. And we're testing to see if P1 is less than P2. We're testing to see if P1 has a lower infection rate than P2. So my test stat, my TS is negative 12.34. So my TS is negative 12. Sorry, my mic cut out there. Negative 12.34 with random lines showing up evidently still because it's really ticking me off. There we go. I wish I knew how to get rid of that. So, mic check here for a second. Okay, good. And then my p-value was 0. Now, is my p-value actually 0? No. If you look it up, bless me, sorry. If you look it up in your z-score table, you'll find that the p-value actually isn't 0. It's like 0.0001. So if your calculator says the p-value is 0, it's just estimating. It's just rounding because it can't handle how small it actually is. So we're going to put not 0 because it really can't be 0. My p-value is 0.0001. That's kind of the bare bones estimate we use when our p-value is very, very, very small. If you want to be super accurate, you could say that it's less than 0.001. You could say that's less than 0.001, but you shouldn't put down that it's 0, even if your calculator says to, because you should know that's really not truly 0. It's just really, really, really small. Okay, it's about that whole ethical stats thing. And then down here we have my pooled sample proportion is 0.068. So this is both sample proportions put together is 0.068. So I can write that down. I really don't need this too much, but it's helpful to know what that number is because you don't still want to know, is this number just randomly there? No, it's helpful to know what the numbers actually mean, even if you don't use them. That way you don't think there's just random information on your screen. But I don't really need that right now. Now my critical value, I believe they say that they're using, let's go back here for a second. They're using a Actually, don't say. That's weird. We're going to assume that they're going to be using a 0.05 significance, even though they don't tell me here. So we're going to assume that my alpha is 0.05, which means that we're going to assume that my critical value is, in this case, it's a left tail test, so we're going to assume that my critical value is negative 1.645. Right? Again, if it's a left tail test, I'm going to assume the negative critical value version of whatever my alpha gives me. So, do we reject or do we fail to reject? Well, if we compare our p-values here, 0.0001 is definitely less than 0.05. So in this case, we would reject. Oh my gosh, every time. I'm just doing this out of, you know, I don't know what the word is. I'm just doing this out of spite here because I just don't want the computer to have the satisfaction of drawing a random line through my 5. But anyway, off topic. Don't want to see me have a mental breakdown right now. My p-value is less than my significance level, right? So this data is significantly rare to reject the claim, the null hypothesis rather. So we're going to reject HO. Basically, again, to put into reference here, this is saying that this event is too rare to have happened, assuming that HO is the situation. So if P1 was actually equal to P2, if there was no difference, then the chance that I had this outcome occur is less than 1%. And that's a very rare chance of happening. So what's more likely is that this is not true, and that this is more true. This is more likely. So we would support my claim in this case. We would support the claim. Oh my gosh. Sometimes you just can't even anymore. We would support the claim that the vaccines do promote a lower infection rate than the placebo, or AKA than people who don't have anything, based on this data here. Now, once again, people would say, well, stats is really good at applying to the whole group, but it really doesn't apply too much to the individual. And there is some truth to that, especially when we have health things. This is why health stuff is so heavily statistically based at one part, and also so easy to pick apart even with stats at the other version, because everybody's health is so different and so specific that sometimes the statistical claims, even though they're completely true and completely accurate, don't apply to that person because of their unique case. So again, whenever you're dealing with health stuff like this, now again, vaccines are kind of a tried and true thing. Vaccines are there for a reason because they work. But that's why, again, all this health information stuff, we have a lot of health examples when we're doing this, because you want to be very clear about what you're doing with your putting stuff in your body, right? But at the same time, since each person's body is different, everybody has some sort of excuse as to why the stats wouldn't apply to them, even when for some of them it actually would. So again, you have to be very careful. This is why knowing how to communicate with numbers and knowing how to communicate with stats is important if you're ever in a health or healthcare field, because you want to be able to communicate effectively what the person's getting themselves into. If you're recommending a treatment, or if you're recommending a vaccine or a antibody, whatever, you want to make sure you're clear about what the science says that could or could not happen to that person, right? So anyway, that's it for this video. Like I said, the heavy lifting's done in your calculator. You just have to know how to interpret the results. Okay, you're kind of uh, outsourcing your work to the calculator, but you have to make the ultimate decision about what those numbers mean. Right? This is not. I'm not here to pick you on part as can you memorize these long formulas and plug numbers in correctly and do all these arithmetic tricks. I'm here to see, can you actually interpret the results of your data. So hopefully this video helped you out. I will hopefully see you later, and have a good day, night, or whenever you're viewing this.